Welcome back to the Deep Dive. Our mission here is to take the dense, fascinating sources you provide, the historical texts, the biographies, the scientific papers, and, really distill them into the essential knowledge you need to be truly well-informed.
And today we are diving deep into a figure whose face is, it's on every chemistry classroom poster in the world.
Right, Dmitri Mendeleev.
But for most people, the story just stops there.
It does. You ask anyone who he was, and they'll say, oh, he's the father of the periodic table. And that's it. End of story.
But that's the challenge, isn't it? Because the sources we've reviewed, they paint a picture of this relentless polymath. A Siberian chemist for sure, but also a pioneering oil economist, a foundational physicist.
And the architect of Russia's entire system of weights and measures. It's an incredible breadth.
The sources show he was driven by this one single unifying force, a hunger for systematic order.
Whether he was organizing the elements or, standardizing vodka production, well, we'll get to that myth later.
Right. But it was always about seeking these predictive laws in the chaos.
Exactly. So our deep dive today moves beyond the classroom chemistry. We are unpacking the totality of the man.
We're looking at the scientific genius, yeah, but also the revolutionary industrial thinker, the dramatic personal life that actually cost him recognition at home.
And a few of those popular myths that we really need to set straight.
We're drawing from biographical accounts to see how his whole expansive career was, at its core, this fundamental search for both truth and utility.
Okay, so to understand the sheer audacity of his later genius, we have to start at the very beginning. And that beginning is a testament to just incredible resilience.
It really is. We're talking about very humble Siberian origins.
Dmitri Ivanovich Mendeleev was born in 1834, not in some cosmopolitan hub like St. Petersburg, but way out in a small village called Verkhny Armzyany near Tobolsk.
And that geographical isolation is key. So is the family's economic situation. The sources note he was the youngest of a massive family.
Massive is the right word. The exact number is kind of disputed, historically.
It is. It ranges from, 13 reliable survivors to maybe 17 children that his mother reportedly bore. But what's clear is the scale of the household.
And the crisis they were plunged into.
A huge crisis. His father, Ivan, was a local school principal, and he went blind, which back then meant he immediately lost his job, his livelihood.
So the father's income is just gone, and the family is facing immediate, serious financial strain.
And this is where we meet the central figure of his entire early life. His mother, Maria Dmitrievna Mendeleeva.
She seems like an absolute force of nature.
She was. The sources are clear on this. She was the one who kept the family afloat and later the one who drove Dmitri's entire education. She was remarkable, an educated woman from a prominent merchant family.
And her response to the crisis wasn't passive at all?
Not in the slightest. To support this enormous family, she took the really proactive step of reopening and managing her family's abandoned glass factory.
Which is just incredible to think about. This isn't just a small effort to make ends meet. She's effectively running an industrial enterprise.
In the middle of Siberia. And this must have given young Dmitri this very early, very practical exposure to industrial chemistry, to production.
That hands-on experience with something like glassmaking had to have shaped his later thinking on, statecraft and resource management.
No question. But then tragedy strikes again. After all her work to get the factory running,
it burns down.
Destroyed by fire. And Dmitri was only a teenager at the time. It's this profound cycle of catastrophe and just sheer determination that seems to have forged his character.
And his mother's legacy wasn't just practical, it was intellectual.
Oh, absolutely. The biographies all confirm that she was the one who encouraged him to patiently search divine and scientific truth. She saw his unique gifts and prioritized them above everything else.
She really instilled in him this idea that learning was the ultimate goal, non-negotiable.
And that conviction led to this incredible journey, the cross-Russia pursuit of an education.
After his father's passing and the loss of the factory, Maria makes this momentous decision. She takes 15-year-old Dmitri in 1849 and travels the immense distance from Siberia all the way to Moscow.
And we really need to pause here and just appreciate the magnitude of that journey in the mid-19th century.
Right. This is not a quick train ride.
No, this was a monumental undertaking. Weeks, maybe months of incredibly arduous travel for a mother and her son, driven by, desperation and hope.
And initially, all that effort was met with rejection.
Total rejection. The sources are very clear that Moscow University just denied his admission. Flat out.
Can you just imagine the frustration, the emotional weight of traveling all that way across an empire just to be told no?
It would have crushed a lesser person, but Maria, she pressed on. They went to St. Petersburg.
And there, they finally had some success.
Yes, she managed to secure him a place at his late father's alma mater, the Main Pedagogical Institute, in 1850.
But his struggles weren't over. Shortly after he graduated, his health completely failed him.
He contracted tuberculosis, a very, very serious diagnosis at the time.
A genuine health crisis that forced a dramatic change of scenery. He had to move south.
To the Crimean Peninsula, yeah. He took up a position as a science master at the Simferopol Gymnasium in 1855, a much warmer climate.
And this 2-year period, which often gets glossed over, was basically a necessary reset for his health.
It was. By 1857, he had fully recovered and was able to return to St. Petersburg, ready to resume what turned into a very high-intensity academic career.
And from that point on, his early scientific foundations were just established incredibly quickly.
He immediately focused on cutting-edge research. He took international research trips, spending time in Heidelberg from 1859 to 1861.
And he wasn't just observing there, was he? He was actively contributing.
Oh, he was right in the mix, studying physical chemistry. His research was highly specific, very technical. He was looking at the capillarity of liquids and the precise workings of the spectroscope.
Which was still a very new, very powerful instrument for chemical analysis back then.
And this is critical because it shows he was mastering both the classical techniques and the emerging tools of instrumentation. It set him up perfectly for his later systematic work.
That grounding paid off almost immediately.
Instantly. He earned his first real widespread recognition by publishing his textbook Organic Chemistry in 1861.
And it won the prestigious Dmitri Prize, which was a huge academic honor in Imperial Russia.
From there, his career trajectory just rocketed upward. He got a professorship at the St. Petersburg Technological Institute in 1864, then moved quickly to St. Petersburg State University in 1865.
And in that same year, he earns his Doctor of Science degree.
He does. And his doctoral dissertation title is something we have to flag now.
On the combinations of water with alcohol.
Precisely, because that title is the little spark that ignites one of the great enduring myths about him, which we will definitely come back to in detail.
But just looking at his institutional impact, his return to St. Petersburg was profound.
It wasn't just about accumulating titles for himself. By 1871, Mendeleev had taken the chemistry department at St. Petersburg State University and transformed it.
Into what?
Into an internationally recognized center for advanced research. He basically created a hub that drew the best students and scholars from all across Europe. He wasn't just an academic presence, he was an institution builder.
Okay, let's transition now to the moment that changed chemistry forever. But before we get to Mendeleev's breakthrough, let's set the stage. What did the world of chemistry actually look like in the early 1860s?
Intellectually speaking, it was a mess, a complete mess.
A collection of facts with no theory?
Exactly. By 1863, there were only about 56 known elements, and they were still being discovered at a pretty steady clip, about one new element per year. So the information was growing and growing, but the structure was totally absent.
So chemists had this rapidly expanding list of ingredients for the universe, but no recipe book, no framework to organize them.
It was a descriptive science, like you said, not yet a predictive one. And Mendeleev was definitely not the only person searching for that structure.
We absolutely have to acknowledge the attempts made by his contemporaries. The ground was fertile for this kind of discovery.
Very fertile. You had people like John Newlands in England. In 1864, he described his law of octaves.
The musical analogy, right?
Right. He noticed that if you arrange the elements by increasing atomic weight, their properties seem to repeat every 8 elements, just like musical notes in an octave.
And Newland's work, it was a genuine step forward. He even identified the potential for new elements like germanium. But it was heavily criticized, even mocked at the time. Why did it fail to get any traction?
Well, because it lacked consistency. And crucially, it lacked predictive power across the whole spectrum of elements. The octaves analogy worked okay for the lighter elements, but it just broke down completely as you moved into the heavier ones.
So the system seemed arbitrary.
It did. It felt forced. And while Newlands was eventually recognized for his insight in 1887, his initial failure was because the system was too rigid and, at the end of the day, just descriptive.
And then there was Lothar Meyer in Germany, who was, you could argue, Mendeleev's closest rival in this race.
Absolutely his closest rival. Meyer published a table with 28 elements classified by their valence in the exact same year, 1864.
And by 1868, his version of the table was almost identical to Mendeleev's.
Almost identical. But here is the critical, defining difference that separated the two of them and secured Mendeleev's legacy forever.
Was it?
Meyer's table was passive. He used it to describe the relationships between the elements he already knew. He made absolutely no predictions for elements that hadn't been discovered yet.
So Meyer was descriptive, Newland's system was flawed?
And Mendeleev was prophetic. That's the difference.
Let's get to the genesis of his periodic law then. It's fascinating that it wasn't born out of some, abstract theoretical quest. It came from a practical need.
That's one of the most remarkable parts of this story. He was writing his definitive 2-volume textbook, Principles of Chemistry, between 1868 and 1870.
And he needed a way to teach it.
He couldn't teach his students inorganic chemistry effectively without a logical, systematic way to classify the elements. The textbook literally forced the discovery. He needed a way to organize his thoughts, and he ended up creating a universal law.
Which leads us to that legendary anecdote, the dream.
Ah, the dream. It's a beautiful piece of scientific folklore, reported by his friend in Ostrancev. Mendeleev claimed he saw the entire arrangement, the complete periodic system, in a dream.
And he just woke up and wrote it all down.
Woke up, immediately transcribed it, and apparently only needed to make one small correction later on.
Whether that was a literal dream or just a dramatic retelling of a sudden subconscious breakthrough after months of intense mental sorting, it definitely captures that eureka moment.
It does. And the formal announcement followed very quickly. It was presented to the Russian Chemical Society on March 6, 1869. The title was The Dependence Between the Properties of the Atomic Weights of the Elements.
And this presentation, it wasn't just a table of elements. It was more like a manifesto.
It was a manifesto. It contained the famous 8 pillars of the periodic law, and they are the core evidence of his genius. We really need to spend some time here detailing what these pillars actually declared to the scientific world.
Let's do it. These 8 points are what elevate his work so far above everyone else's attempts.
Okay, so Pillar 1. This established the fundamental relationship. Elements, when you arrange them by increasing atomic weight, show an apparent periodicity of properties.
That's the cornerstone, the basic definition of the periodic law.
Exactly. Then, point 2 focused on grouping. He showed that similar chemical properties appear when the atomic weights are either very similar, think of metals like platinum, iridium, and osmium, or when they increase in a regular way.
Like the alkaline metals, potassium, rubidium, cesium.
Right. This justified grouping the elements into what we now call families or groups.
And point 3 tied that grouping back to chemical behavior.
Yes, stating that the arrangement correlates with their valencies and their distinctive chemical properties. He was establishing those familiar patterns you see in a series like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. He was making sense of the reactive potential of everything.
Point 4 is a bit of a fascinating detour, almost into cosmology.
It is. He observed that the most widely diffused elements, the ones that are most common here on Earth, and, he presumed, in the universe, also happen to have the smallest atomic weights.
So he's linking the microscale pattern of his table to the macroscale composition of the cosmos.
He's thinking big. And then came point 5, which is really the philosophical core of his law. He declared, and this is a near quote, "The magnitude of the atomic weight determines the character of the element."
Just as the magnitude of the molecule determines the character of a compound body.
Precisely. This was him declaring that his table wasn't just a convenient chart. It was a universal determinative law. Atomic weight dictates identity.
And that conviction, that absolute certainty, leads directly to point 6. This is the revolutionary step.
This is the one that sets him apart from Meyer and Newland's. The crucial prediction. He stated confidently that we must expect the discovery of many yet unknown elements.
He didn't just leave it at that, did he? He wasn't vague.
Not at all. He got highly specific. He predicted 2 elements that would be like aluminum and silicon, and even stated their atomic weights would fall somewhere between 65 and 75.
So he deliberately leaves gaps in his own table.
And in doing so, he turns those gaps from signs of incomplete knowledge into signs of structural necessity. He's saying the gaps prove the system. They don't undermine it.
That is astonishing confidence. He's saying the elements might be missing, but my system is complete. But for me, point 7 is the real intellectual paradigm shift.
Yes. The idea that atomic weights could be amended by knowing the elements around them.
This is where his genius truly shines. He used this logic to challenge the accepted atomic weight of tellurium.
Right. At the time, tellurium's weight was measured at 128. Iodine was 127. So if you went strictly by weight, tellurium would come after iodine.
But chemically, that made no sense. Tellurium clearly belonged to the group with oxygen and sulfur before iodine and the halogens.
So Mendeleev just argued that the accepted weight had to be wrong. He suggested it must be somewhere between 123 and 126.
Yeah, he was actually wrong about the exact measurement. Tellurium's modern weight is 127.6, but he was profoundly right about the order.
He was, and this is the key. He argued that the chemical properties and the necessary periodicity of the system must take precedence over imprecise measurement data. He was subordinating the observer's data to the system's law.
That shift, prioritizing the structure over the measurement, is what turned the periodic table into a fundamental law of nature.
And finally, point 8 just summarized the whole system's utility. The characteristic properties of elements that haven't even been discovered yet could be precisely foretold from their calculated atomic weights. It cemented the table as the ultimate predictive tool.
And the power of that prediction became reality shockingly fast.
Incredibly fast. He had accurately predicted the properties of 3 unknown elements, and he gave them these temporary Sanskrit names, ecosilicon, ecoaluminium, and ecoboron,
which were later discovered and named germanium, gallium, and scandium.
And his predictions weren't just vague guesses. His detailed forecasts for ecoaluminum, which became gallium, were just stunning. He predicted its density, its melting point, its behavior in solution.
And they were virtually identical to the properties that were later measured by its discoverer, Paul-Émile Lecoq de Bois-Badran, in 1875.
That level of prophetic accuracy just silenced any remaining critics. It was undeniable proof.
He also used the system to correct what was already known, the accepted values for uranium, for instance.
Before his work, uranium was thought to have a valence of 3 and an atomic weight of about 120. But when he tried to slot it into his table based on those numbers, it just didn't fit. It ruined the whole structure.
So he just decided the prevailing measurements had to be wrong.
He did. He doubled both values, proposing a valence of 6 and an atomic weight of 240. This placement fit perfectly into the system. And of course, the modern atomic weight of uranium is 238. He was right.
He didn't just organize the known, he corrected the misunderstood.
A perfect way to put it.
Let's talk about the nomenclature for a second. The Sanskrit prefixes, Eka for 1, Dv for 2, Tri for 3. Why Sanskrit?
This is such a beautiful piece of intellectual history. It ties his scientific structure to this ancient, systematic way of thinking. The sources suggest he was honoring a friend of his, an eminent Sanskritist named Otto von Bittlink.
But it's deeper than just a tribute to a friend, isn't it?
Much deeper. Ancient Indian grammarians, particularly a figure named Peeni, were famous for using these incredibly rigorous, two-dimensional, systematic patterns to organize the sounds of language.
So Mendeleev's use of Eka is an explicit connection between his chemical matrix and a tradition of systematic order that's millennia old.
Yes. He's linking the organization of matter itself to the organization of language. It shows he saw his work not just as chemistry, but as this deep, philosophical endeavor into fundamental structure.
And even after this immense triumph, he knew the system wasn't finished.
No, he was puzzled by the lanthanides, the rare earth elements. He couldn't quite figure out where to place them. And he correctly anticipated that the table would eventually need another entire row of heavy, complex elements.
Reactinides.
The actinides, which only really appeared much later as new elements were created artificially in labs. He established this dynamic, living framework that could absorb future discoveries and corrections. It's so fitting that he called his discovery the periodic system.
Because it wasn't just a table.
It was a system that dictates law, not just a collection of data.
Okay, so let's now fulfill the promise of this deep dive and explore the other half of Mendeleev's life. Because his scientific curiosity was absolutely not limited to the elements.
Not even close. He was deeply and practically involved in the political and industrial future of the Russian Empire.
His dedication to building up Russia's scientific capacity was clear from early on. He was a co-founder of the Russian Chemical Society in 1868.
Helping to institutionalize the very field he was in the process of revolutionizing. But his interests were just too broad to be confined to a single discipline.
The Russian chemist Lev Chugayev characterized him perfectly. He said Mendeleev wasn't just a genius chemist, but also a first-class physicist and a fruitful researcher in so many adjacent fields.
And that versatility, it all stemmed from his systematic approach to problems. He applied that same thinking everywhere.
His intellectual rigor was also matched by a willingness to jump into public philosophical debates.
Oh, he was a fierce rationalist. He argued very strongly against the scientific claims of spiritualism, which was surprisingly fashionable among the Russian elite at the time.
He wasn't afraid to call it out.
Not at all. He called metaphysical idealism ignorant superstition, and he was genuinely concerned about the effect it was having on serious scientific study in Russia.
So he's not just a lab chemist. He's actively out there championing empirical thinking, using his scientific reputation to enforce intellectual standards.
And that same drive for standardization and fundamental laws, it just permeated his work in physics. He made theoretical contributions that really anticipated later breakthroughs.
Like his work on the absolute boiling point.
In 1861, well before the standard was set, he came up with a definition for it.
How did he define it?
He defined it as the temperature at which the cohesion of a liquid and its heat of vaporization both become equal to zero. It's the point where the liquid transforms into vapor, regardless of pressure or volume.
He's basically describing the point where the distinction between liquid and gas just vanishes.
He is. It's a moment of unity between the states of matter. And this definition strongly anticipated Thomas Andrews' formal conception of critical temperature, which became one of the most important concepts in thermodynamics later in 1869.
So he's finding unity across the states of matter, just like he found unity across the elements.
He also developed a formula for the expansion of liquids with heat, which was very similar to Gay-Lussac's law for the expansion of gases, again, trying to find a universal law that covered both liquids and gases.
But maybe his most peculiar excursion into theoretical physics was his attempt to fit the very structure of the cosmos into his periodic law. I'm talking about his ether hypothesis.
This is such a great example of him trying to apply his system to absolutely everything, even speculative physics.
So what was the idea?
He believed that if his periodic table was truly complete, then there must be two inert chemical elements that were even lighter than hydrogen.
Lighter than hydrogen.
Yeah. He hypothesized that the lighter of these two would be an all-penetrating, almost massless gas. And this, he proposed, was the aether, which physicists at the time still thought was necessary for light to travel through space.
And the other one?
The slightly heavier one he called coronium. Now, this idea was eventually abandoned with the rise of quantum mechanics, but it just shows his absolute dedication to making the periodic system the ultimate organizing principle for everything.
All right, let's pivot now to his very practical role as a servant of the Russian Empire. His involvement in industry, especially petroleum, was groundbreaking.
His work for the state was profound. He investigated the composition of petroleum, and he was deeply involved in helping to establish Russia's very first industrial oil refinery.
This was a direct output of his drive to modernize Russia's industrial base.
And it leads to probably his most insightful non-chemical observation. He recognized very early on that petroleum was far more valuable as a raw material than it was as just fuel.
This is the famous quote, right?
It is. He famously remarked that burning crude petroleum, just for heat or light, would be akin to firing up a kitchen stove with banknotes.
You have to put that in context. In the 19th century, oil was mainly seen as a replacement for coal or whale oil.
And Mendeleev saw its potential as a complex feedstock for thousands of petrochemical products. He recognized its vast economic value for chemical synthesis, a realization that was decades ahead of its time.
Did he also have a controversial take on where oil even comes from?
He did. His insight wasn't just practical, it was theoretical geology. Mendeleev was a staunch proponent of the abiogenic hypothesis.
Meaning oil isn't from dead dinosaurs.
Exactly. He concluded that hydrocarbons do not originate from decayed biological matter, which is the dominant theory today, but instead formed deep within the earth from inorganic materials reacting under immense pressure.
He wrote that petroleum was born in the depths of the earth, and it is only there that we must seek its origin.
And you can see why a chemist who thought in systems would lean that way. He saw the systematic presence of hydrocarbons in various deep geological layers and believed their sheer quantity couldn't be easily explained by surface-level biological decay.
An inorganic, deep earth origin probably seemed more fundamentally systematic to him.
I think so. Beyond oil, he was a key figure in national economic policy. He was concerned with the merchant navy, advising on ship design and trade routes. He extensively researched agricultural productivity, especially the efficacy of chemical fertilizers.
He was aiming to lift the entire Russian economy.
And politically, he championed a protectionist stance on trade.
How so?
In 1891, he successfully convinced the Ministry of Finance to impose temporary tariffs on foreign imports. It was an explicit protectionist policy designed to shield and foster Russia's new infant industries, textiles, metals, chemicals.
Let them grow and get competitive before opening them up to the full force of Western European industry.
Exactly. He was an economic strategist committed to internal development, and his commitment to science and to his students was so fierce that it actually cost him his professorship.
He resigned.
He resigned from St. Petersburg University in 1890 after a very heated dispute with Ministry of Education officials over their heavy-handed treatment of university students. He sacrificed his top academic post over a matter of principle.
Which is incredible. But he didn't retire. His focus on order and standardization led him directly into his final and profoundly important career role.
That was his appointment as director of the Bureau of Weights and Measures in 1893, a post he held until his death.
It sounds kind of mundane, Bureau of Weights and Measures, but his impact there was transformative.
Absolutely crucial for modernizing Russia. He is credited with introducing and fully institutionalizing the metric system across the entire Russian Empire. This meant standardizing the fundamental prototypes, the exact meter, the exact kilogram.
And all the measurement procedures across a vast nation that was filled with inconsistent local measures.
It required the exact same systematic, law-enforcing mindset he applied to the periodic table. If you want a modern, unified industrial state, you need universal, precise standards, and Mendeleev provided them.
And just to round out his sheer breadth of work, he even delved into military chemistry.
He did. He invented something called pyrocolloidin, which was a nitrocellulose-based smokeless powder commissioned specifically by the Russian Navy. The Navy ultimately didn't adopt it, but it's just more proof of his ability to pivot his genius to solve any high-stakes technical problem put in front of him.
Okay, so the public record of his scientific and state service is, it's impeccable. But the sources reveal this really turbulent personal life that created immense institutional friction for him back home in St. Petersburg.
It really did, and it culminates in perhaps the most famous snub in the history of science.
The personal drama, it really began with what became known as the bigamy controversy.
Mendeleev was known for being intense, and in 1876 he became, well, the sources use the word obsessed, with a young art student named Anna Ivanovna Popova.
And the courtship was highly dramatic.
Very. He proposed to her in 1881 and reportedly threatened to commit suicide if she refused to marry him.
Which led to a very serious scandal.
It did. He married Anna Popova in early 1882. The problem was, his divorce from his first wife, Fyazva, was only formally finalized by the church 1 month after the second marriage took place.
So technically, he was a bigamist.
In the eyes of the very powerful Russian Orthodox Church, he was. The church legally mandated a waiting period of at least 7 years before a lawful remarriage could happen after a divorce.
And the controversy had real, lasting consequences.
Oh, absolutely. While the second marriage was eventually recognized after a large payment to the local priest, which caused its own public outcry, the scandal, combined with his frequent political disagreements, contributed directly to his failure to be admitted to the prestigious Russian Academy of Sciences.
Which is just bizarre when you think about it.
Yeah.
This is a man who was elected a foreign member of the Royal Society of London in 1892. He was honored all across Europe with the Davy Medal and the Copley Medal, the highest honors in British science.
And yet he was considered too socially and politically disruptive for his own nation's premier scientific body. It really highlights the difference between international scientific merit and the conservative social machinations of the imperial Russian establishment.
And that internal snub was really just a precursor to the great international disappointment, the Nobel Prize.
The Nobel snub is just a notorious tale of internal rivalry in politics. Mendeleev was nominated 3 times in the final years of his life, 1905, 1906, and 1907.
In 1906, he was agonizingly close.
So close. The Nobel Committee for Chemistry unanimously recommended him for the prize, specifically citing his revolutionary periodic system. Everything was set for him to finally get the award.
But then, at the final full meeting of the Swedish Academy, things went sideways.
Peter Classen, who was a dissenting member of the committee, strongly opposed the recommendation and proposed the French chemist Henri Moissan instead.
And the real political muscle came from a scientist who wasn't even on the committee.
Svante Arrhenius. He'd won the Nobel in 1903, held massive influence, and he vehemently argued against Mendeleev. The official reason he gave was that the discovery of the periodic system was too old to be acknowledged in 1906.
But the sources suggest that Arrhenius's motivation was anything but objective. It wasn't really about the date of the discovery, was it?
Not at all. Contemporaries were convinced Arrhenius was motivated by a personal grudge.
A grudge over what?
Mendeleev had been a very public, very outspoken critic of Arrhenius's electrolytic dissociation theory, especially on the nature of solutions. This was scientific rivalry taken to the level of institutional sabotage.
So the Nobel Prize, this award intended to honor the greatest achievements in science, was derailed by one man's personal vendetta.
That's the sad reality of it. After a heated debate, Moissan won the final vote by the slimmest possible margin, just one vote. And Arrhenius reportedly opposed Mendeleev's nomination again in 1907, ensuring that the father of the periodic table died without the world's most famous scientific honor.
It's just a painful reminder that even at the highest levels of recognition, politics and grudges can sometimes prevail over pure merit.
It really is.
Okay, before we close the book on his incredible life, we absolutely have to tackle the myth that shadows him in popular culture. It's probably more pervasive than his oil work or his metrology.
The great vodka origin myth.
Exactly. The story is a marketing powerhouse.
Yes.
You see it from certain vodka brands. Russian Standard is a big one, claiming that Mendeleev, through his scientific research, established the 40% alcohol standard for Russian imperial vodka.
It's a lovely picture, isn't it? The world's greatest chemist perfecting the national drink.
But what is the documented truth, based on the historical records?
The myth is unequivocally 100% false. The historical documents are crystal clear on this. The 40% standard, technically 40 degrees by volume, was introduced by the Russian government way back in 1843.
And Mendeleev was how old then?
He was 9 years old. He had absolutely zero influence on its adoption.
So where's the confusion even come from? It seems to trace back to two separate facts that just get wildly conflated over time.
That's exactly it. Fact one is his 1865 doctoral dissertation, which had that rather dry title, A Discourse on the Combination of Alcohol and Water.
People hear that title and they immediately think vodka.
Of course. But the dissertation itself had nothing to do with vodka. It focused entirely on the volume changes and properties of high-concentration alcohol solutions, generally above 70%, stuff relevant for medical or industrial use, not for the popular drink of the day.
In fact, too, is his later role as director of the Bureau of Weights and Measures. The myth suggests he set the quality standard while he was there.
Which is another complete conflation. The bureau he directed from 1893 dealt with standardizing physical instruments and measurements for trade. The kilogram, the meter, things like that. It had absolutely no jurisdiction over setting quality standards for specific products like alcohol strength.
His role was about measurement accuracy, not regulating the national beverage.
Precisely. So Mendeleev's connection to vodka is purely academic studying high-strength ethanol solutions and bureaucratic standardizing the weights that might be used to measure grain or liquor for trade. He was interested in metrology, not mixology. The myth endures, but the facts are clear.
So we've covered just an immense range of influence today. Dmitri Mendeleev began his journey defined by his mother's resilience in the middle of Siberia.
She went on to organize the entire physical universe into a predictive system, champion Russia's industrial future in oil and trade policy, and define the standards of measurement for a vast empire.
And all the while battling these institutional snubs and personal scandals.
I think the unifying lesson here, really, is that his scientific triumph, the periodic table, it wasn't some isolated burst of brilliance. It was the product of a deep, lifelong commitment to systematic order.
And a belief that underlying laws govern all chaotic appearances.
Exactly. His core genius lay in the intellectual audacity to use those patterns for prediction. He didn't just catalog what was known.
He forced the world to acknowledge the existence of the unknown, the Ika elements.
And critically, he forced other chemists to prioritize the law of periodicity over their own flawed, measured data for elements like tellurium and uranium. He's the one who transformed chemistry from a descriptive science into a predictive one.
A truly fundamental shift. And as you move forward with this knowledge, we want to leave you with a final provocative thought about the complexity of the man.
Mendeleev died in 1907 from influenza. His last recorded words to his physician, which were reportedly a quote from a Jules Verne novel, were, "Doctor, you have science, I have faith."
Which is such a fascinating final statement.
It is. When you consider his rigorous empiricism, his championing of systematic science, and his fierce lifelong battles against things like spiritualism, against superstition.
What does that final line truly reveal? about his personal synthesis of it all. Did the man who sought to scientifically define all matter find, in his final moments, a boundary between empirical knowledge and profound belief?
It's something to truly mull over.
A profound question indeed. We hope this deep dive into the polymath genius of Dmitri Mendeleev has been enlightening.
Until the next time, we'll see you then.